In the last section, ladies and gentlemen, we were talking about mapping the early universe. And we talked a little bit about the early COBE missions. And the early COBE mission produced an energy distribution around the universe that looked something like this. Now, this was the early 1990s. By time 1992 occurred, there was, and that's still in the early 1990s, there was a better map of the background radiation in the universe. The COBE satellite took such good data, and it was analyzed with such care by George Smoot and John Mather, that this picture is the picture they got of the early universe. Now, the red is the Milky Way galaxy. It is close to us. There's a lot of heat given off by it because of the fact that it is so close. But if we look way back to these tiny little 3 Kelvin temperature fluctuations coming from space, these two gentlemen were able to detect variations in temperature in this early universe, meaning about 400,000 years after the Big Bang, that these temperature fluctuations were as small as 30 microkelvin. Now that is 30 times 10 to the negative 6 Kelvin. Incredibly tiny fluctuations in energy. Because of the massive amount of work that went into this, George Smoot and John Mather shared the 2006 Nobel Prize for detecting that radiation. Now, this is a picture of me. I had the honor of meeting George Smoot, and I got my picture taken with him at a physics conference a couple of years back. And yeah, I got a stupid look on my face because I'm sitting there going, oh my God, I'm standing next to George Smoot. So that was a really big deal for nerdy little me. But just to show you how we have advanced through time, 1965, Penzias and Wilson said, hey, there's microwave background radiation coming from all directions and it all looks the same. By the early 1990s, with COBE Map, with Smoot and Mather's work, we had a lot more detail about where this microwave background radiation was coming from. Now, you might be saying, whoopee-doo, why do I care? Well, folks, where there is high concentrations of energy in the early universe, that's what turns into galaxies. And so this is like baby pictures of you, me, and the entire universe. That's what this is. That is scary, nifty, cool. By 2012, there was a huge, massive improvement to the COBE maps. This was called the WMAP, the Wilkinson Microwave Anisotropy Probe. Anisotropy means deviations from isotropy. Isotropy means everything's the same everywhere in all directions. Anisotropy is looking for slight variations, tiny little variations in temperature in that early universe. Now, it took 9 years of data with this satellite to actually collect and then analyze it to get this picture. Those tiny little red spots, those are hot spots in the early universe that turned into galaxies. What are these areas right here? We've talked in the last chapter. Those are the voids that we see today. So this is the underpinning structure of the universe at its very beginning. It's kind of like seeing a building before the sheetrock and the walls are on. You can see the 2x4s. You can start to see the rooms are stubbed out and where the kitchen's going to go, but it's not covered up by other things. That's what we're looking for with these early microwave pictures. This satellite image showed deviations of 0.0004 Kelvin, tiny differences in temperature, which the fact that we can measure that so carefully is absolutely crazy nutty. This is just a close-up of the WMAP, one of the most beautiful pictures ever created in science. This is the baby picture of the universe. Hot areas, these all turned into galaxies and clusters of galaxies, and these are the cold areas. Those are those great voids. Well, the Americans were working on the WMAP. The European Space Agency was actually working on the Planck map, and they created a much more detailed picture of the early universe. This also took a decade's worth of data to create. Temperature differences between the reds and the blues are incredibly, incredibly small. And one more time, these big areas, those are going to be clusters of galaxies, not just individual stars, clusters of galaxies. So what have we learned from the last 40 years of mapping, from the COBE map in the 90s through the W map and then the Planck map? Here's what we've discovered. First off, the more detailed images have given us a lot more just data about what it looked like. We know more about the density of matter. Normal baryonic matter, okay, when I say baryonic matter, I mean matter that contains protons, neutrons, and electrons. Normal particles that you and I are used to. And the early definitions, the early distribution of dark matter. Because if you remember from past chapters, the fact that dark matter creates this structure or this scaffolding and that galaxies form on this sort of soap bubble outer edges. And we can see that soap bubble structure long before the universe was very old at all. We're still looking at a universe that's about 400,000 years old, right at the time of first light. As soon as light could be produced, that's what we're detecting. We're also getting a lot more information about the density of energy. Normal energy, where is energy in great concentrations, these hot spots, and where is energy not in great concentrations? So we're still learning a lot about dark energy and dark matter, but these maps are giving us so much more insight into what that looks like. And if we go back to that puddle story, the areas where the puddle is thick is like areas where there's a lot of heat and there's a lot of energy. And the areas where the puddle is very, very thin, those are those cool areas. And this gives us kind of a detail of what was there long ago and far away. We now know, due to these maps of the early universe, that the universe is pretty darn close to flat. That means it's balanced between open and closed. It's balanced between a universe that's expanding and a universe that is contracting. A flat universe is one that is kind of holding steady. The steady state theory of cosmology was disproved, but our relatively steady universe is kind of nice, because if we had a universe that was changing very rapidly, we would not be here. There would not be time for evolution to have occurred. So the universe is cool, kind of pretty flat. Not exactly, but pretty flat. We now know a lot about Hubble's constant. Hubble's constant through time has been fine-tuned. That gives us a better idea of the age of the universe, which we now believe with pretty good accuracy is about 13.8 billion years ago, plus or minus about 0.04 billion years. That's pretty cool that we know this number to that amount of exactness. We now know that our Big Bang Theory works. A theory must predict something and then see if that prediction comes true. And time after time after time, the Big Bang Theory matches observations, what astronomers are seeing when they look into the night sky. We now know that there is about 5% ordinary matter. That is stuff that is made of protons, neutrons, and electrons, and about 25.8% dark matter, that mysterious something that is gravitational, that exerts a force of gravity and pulls things inward. We also know that there is about 69.3% of the universe is made out of dark energy. Dark energy is the stuff that is making the universe expand. Do we totally understand these yet? Of course not, but that's half the fun of science, is not knowing everything yet. And these tiny little variations here, those are the seeds of galaxies and clusters of galaxies. When astronomers do computer simulations of what a hot spot in the early universe would look like to produce a galaxy, this is what they predicted, and this is what they saw. Ain't that cool? It is so nifty. That would be an area that would turn into a galaxy. A cold spot was predicted to look something like this, and this is what W map actually saw. So again, it proves that we are not full of beans and that the scientists do have a good idea what's going on. Okay, in the next section, we're going to go through Big Bang Theory, and we are going to take it a second at a time. And how did the universe begin?